Okay, I think we left off on page 18. We did. And I wanted to talk about this right here. In this section, when we talk about the radius and the interval of convergence in the center of the power series, we're using a ratio test to force this to converge. And the rule for ratio test is that when you do that ratio test, like this one over here, it's the limit of the ratio, thank you, of the two terms. The ratio test has to have a limit that's less than 1. That's why this interval of convergence right here happened to be where it was. I don't know that I did a good job saying that out loud yesterday. If everyone was like, where'd the 1 come from? Why is it in between 1 and 1? It's because of the ratio test. So we'll do another example and you'll see how it connects. On this one, if that limit goes to 0, that means that it's always less than 1. And so it converges for everything, right? And so I don't have to worry about what values it goes to. And that's why the interval of convergence goes from negative infinity to infinity, and the radius of convergence is infinite, because it always converges, all the time. Okay? So let's try the next one. We are looking at B. Am I on page 18 still? Yeah, I am. Okay. So the first thing I want to do is list out, expand the power series so I can see the first few terms, okay? So the function that I'm working with, when n is 0, anything to the 0 is 1. So my first term for this one is going to be 1 over 1, or just 1. When n equals 1, I have x plus 1 squared over 9. When n is 3, I have x plus 1. Oh, I'm sorry. This is n equals 0, 1, 2. I'm jumping ahead of myself. Third term, but not what n equals. So 2 times 2 is 4, and I'm over 9 squared. My next term, x plus 1, 3 times 2 is 6, and this is 9 to the third. And it's going to keep going, right? That's my infinite function. If I separate the x term from that coefficient, or constant portion, if you will, what do you notice about this series? Wait, that's times. Times. I'm pulling out the 1/9 and I'm rewriting it. What do we call a series where we have this same thing being raised to a higher power each step? Haha, there we go. So this is a geometric series. And I'm noticing that my common ratio is less than 1. So I don't need to use the ratio test. I can see the ratio, right? And I know that common ratio, it includes the x plus 1, because that's getting that's increasing. The power of that is also increasing. That's what's getting multiplied each time. Okay, so we expanded it. We discovered that it was a geometric series, no ratio test needed. The rule for the ratio test is that our R value needs to be less than 1. Its absolute value needs to be less than 1, which is why we put it between -1 and +1. Not now, Apple. Good morning. We're on page 18 in the notes. So now I'm going to solve this, and it can give me, once I've solved it, I'll be able to see my interval of convergence and my radius of convergence. So multiply everything by 9. I'm going to do something and you're all going to hate it. Remember that this was originally, the original problem was this. Okay. So if I'm thinking of it like this and I multiply both sides by 9 and I'm still looking at the absolute value, and then I'm taking the square root and I'm still looking at the absolute value, I'm allowed to think of this as it's going to eventually get down to -3 is less than x plus 1 is less than +3. I didn't just take a square root of a negative. I'm following through with this absolute value idea. Are you guys okay with that, or you want me to redo my work? Okay. Okay. So now I'm going to subtract 1 in all the places. So -4 is less than x is less than 2. And this is our interval of convergence. So our interval of convergence goes from -4 to 2. I'm using open bracket parentheses right now because I haven't tested my endpoints yet. We haven't talked about that. We will in a minute. And that means that my radius of convergence, I take the length of that from -4 to 2 is 6. And so my radius of convergence is half of the length, which is 3. And where is it centered? I can see it in two places. I see that I have x plus 1, and so my center is at -1. That's ground zero. I can also see if I go halfway in between my interval of convergence, the halfway point is at x equals -1. So I can see the center in two different places here. How are we feeling? All right. Let's try one more on this page. Is there a question? Maybe two more. Yeah, we're going to do two more, I think. Okay, so step one, we're supposed to list out our power series, expand this. So f of x equals, this one is alternating because of the -1 to a power, and it starts off positive. The other part, I'm starting with n equal to 0, so I end up with x to the first over 1 factorial. My alternating, now it goes to negative. My n value is 1 at this step, so I have x to the third and 3 factorial. The 2n plus 1 ends up giving us odd values. My next term is positive, x to the, this is my n equals 2, so 2 times 2 is 4 plus 1 is 5, so x to the fifth over 5 factorial. Alternating, so now I'm back to negative, x to the 7th over 7 factorial, and it's going to keep going. Start looking for these patterns. 2n plus 1 is going to give you odd values. So once you establish the pattern, you should be able to go quickly to expand the rest of the series. The first few times, yeah, it takes us a minute to look at it and think about it, but we should be getting quicker at it the more practice we're doing. Okay, so we are performing the ratio test so that we can find the center, radius, and interval of convergence. Before I perform the ratio test, let's think about where the center is. Do I have x plus a number in parentheses? Nope. So the center is at 0. Okay, so that's taken care of. Now I'm just going to do my ratio test. So I'm doing the limit as n approaches infinity. I have to have n plus 1. So let's think about what happens with that. The absolute value is going to eliminate the -1 to the n component, right? It makes all the terms positive. So I'm going to not include this. I'm not writing it down because my absolute value knocks that out. The 2n plus 1, what happens is I have 2 times n and 2 times 1 plus an extra 1, and I end up with x to the 2n plus 3 because it was 2n plus 1 plus 1. Are you okay with that?
Yeah.
That was something we were making mistakes on when we were doing board work the other day, so just be careful. We don't want to mess up little arithmetic things. And then my denominator is 2n plus 3 factorial. And I multiply by the reciprocal of the original 2n plus 1 factorial over x to the 2n plus 1. I'm going to have to do some manipulation here. Move some stuff around, expand some stuff out. If you're good at it, a lot of people do that as mental math. You actually don't need to show these steps, but some of us, I think we need to see it. So I have x to the 2n times x to the third over x to the 2n times x to the first. I moved all the x's to the left and I expanded that a little bit. Are you okay with it? Okay. Makes it easier to see what cancels, right? And now for my factorials, 2n plus 1 is smaller. So I'm expanding out 2n plus 3, 2n plus 2, 2n plus 1 factorial. There's my absolute value. Here's what cancels. These guys cancel. The factorials cancel. And I can actually cancel one more factor of x. So my limit as n approaches infinity of x squared over 2n plus 3 and 2n plus 2. Ugh, one of those was an n. There we go. Remember, we're ignoring x for a minute. N is what's going to infinity. That means that this is bottom heavy. We end up with x squared times 0, which is 0. So if our ratio goes to 0, it converges for all x values. Negative infinity to infinity is our interval of convergence. Our radius of convergence is infinity. And from up above, our center was at 0. Okay, one more because there's another option. So we have a radius of convergence that we find the values. We have a radius of convergence where it always converges, so it's infinite. And we also have the option for there to be not a radius at all. It only converges at a single value. And so I want to show you what it looks like when we go through that process. So we're going to do letter E. I'm cherry picking the best problems. So for this one, we expand it out. Our f of x is when we plug in 0, 0 factorial, do you guys remember 0 factorial equals 1? So we have 1 times something to the 0 power, which is just 1. Second term, we have 1 factorial times x minus 2 to the first power. Next term, we have 2 factorial x minus 2 squared. Then we have 3 factorial x minus 2 cubed, and the pattern continues. Where is this centered? At x equals 2. Okay, let's do our ratio test. So we're doing the limit as n approaches infinity. We have n plus 1 factorial x minus 2 to the n plus 1 in our numerator, and our denominator is the original n factorial x minus 2 to the n. I'm not going to expand this one. Let's see if you stick with me. N plus 1 factorial over n factorial is n plus 1. You okay with that? Okay. X minus 2 to the n plus 1 over x minus 2 to the n is x minus 2. We're still looking at the absolute value of this, and we're still finding the limit as n approaches infinity. This diverges. This blows up. We have infinity times x minus 2, right? And so that diverges, which means it goes to infinity. So we have no radius of convergence at all. We said that our center was at x equals 2. The radius of convergence is at 0. The interval of convergence is a single number, just 2. And it converges at x equals 2 only. Okay, questions on what's going on there? Cliff notes, not cliff notes. This is a summary of what we all just did. Okay, so if you're going to look back and you want to understand what happened and what are my options, look over here. So the ratio test for power series follows the same rules of convergence that we were just looking at. So if the limit that we get from the ratio test is 0, it converges for all values from negative infinity to infinity, and the radius is infinite. If the limit approaches infinity, the power series only converges at its center, and the radius is 0. And if it approaches a function, the power series converges where that function is between -1 and +1, and possibly at the endpoints. We'll talk about that more in a second, okay? The problem with the endpoints is sometimes they work and sometimes they don't, and the only way to know if they do is to check them. You literally plug them in and check, which we'll get to. Questions were good. All right, get ready because I'm going to make us do some board problems.